Hello students, today we will discuss refraction from the chapter ray optics. What is refraction is, it is the bending of the ray of light when it enters a new medium. So from one transparent medium to another transparent medium, when light passes, what happens is at the interface, that is at the point of incidence, there will be a change of path as well as change in the speed of the light ray. So here in these figures, we can see here in this glass slab, for example, a beam of light is passing through the glass slab, and you can see that its path is getting changed. When it leaves the glass slab also, there is a change of path. Similarly, in this figure over here, the pencil is inside the water and a part of it is in air. So you can see that it has two paths. The light is passing through two directions. That is why you can see it is like it is bended. So this phenomenon is known as refraction. That is the bending of the ray of light when it is passing from one transparent medium to another. The refraction is caused by, light refraction is caused by difference in the refractive index of the medium. Now you see here in this figure, when the ray of light is incidenting at an angle 0, okay, then the ray is straight, it passes like that itself to the next medium. Okay, there is no refraction happening there, it's not deviating. But you can see here in the second part of the figure, you can see that the incident ray is oblique. Then it has a deviation from its original path. This was the original path, from that it is getting deviated. As well as there will be change in the speed of the light ray when it is in air as well as in water. That is caused by the difference in the refractive index of water and air. The refractive index of air is always 1. Air or vacuum, we can take it as 1. Now you observe this figure. This is a glass slab, like the same graphical picture. You can see the incident rays coming over here. There is a normal at the point of incidence. Then this path is called the refracted ray. There is again a normal on the second interface. Then this portion of the ray is called the emergent ray. And what is this one over here is the incident rays extension. So there is a lateral deviation of d, this much lateral deviation is happening, and you can see that the angles are different. This angle is called I, the angle of incidence. This angle is called, you can call it as I1, otherwise this one is R1, the first refraction angle. Then this you can call R2, and this is called the emergent angle E. So what we can see is when the ray of light is falling from less denser medium called air, where n equal to 1, to a glass slab where n usually is equal to 1.5, what is happening is the ray of light is bending towards the normal. That means the angle of refraction is very small. It is bending towards the normal. Now again it is leaving, at this point it is leaving, the ray of light is leaving the glass slab, that is from n equal to 1.5 to again n equal to 1 medium. Then what is happening is again the, what you can see here, the emergent angle is much more than this refraction angle. That means the ray is bending away from the normal. Here it is bending towards the normal, here it is bending away from the normal. Now coming to the next portion, laws of refraction. Like we have studied in the previous previous portion of the lesson, that is there are two laws of reflection you studied. Similarly, there are two laws of refraction also. The first law is very much similar to the reflection laws. The incident ray, refracted ray and the normal lies in the same plane. What is meant by they lie in the same plane is like this, like we have an interface, maybe it is air and water as I'll mark here. Then the ray of light is falling like this, and we have a normal here at the point of incidence, and it will be bending towards the normal because, as you know, water has more refractive index than air. So what is happening is we can see this normal, this incident ray and this refracted ray, all we could draw on the same plane, that is on this screen, the surface of the screen. You don't have to assume like the ray is going inside or it is coming out from. So that is why we say that it is in the same plane. Now the second law is Snell's law. You have learned it in 10th standard. The ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a pair of media and for a given color of light used. So what you have to do is, if for air you are taking N1 as the refractive index and for water you are taking N2 as the refractive index, and you are taking this angle of incidence as theta 1 and this angle of refraction as theta 2. So what you have to do is you have to put N1 sine theta 1 is equal to N2 sine theta 2, because the products will be equal. The refractive index and sine of angle of each angle in that respective medium will be equal to each other. So that is what this shows. N1 sine theta 1 equal to N2 sine theta 2. So here in this case, N1 is air, so that has a value 1. Water is having approximate 1.33 and all. So what will we do here is, for example, sine theta 1 by sine theta 2, if you take, it will give you N2 by N1. N2, if you put N as a value and N1 is 1, then you can say it is N equal to sine theta 1 by sine theta 2. And this theta 1, theta 2 you can even write in terms of your angle of incidence and angle of refraction terms. So what we write is sine I divided by sine R is equal to N. So this is what we learned in 10th standard. So actually speaking, this has to be N21. That means refractive index of second medium with respect to the first medium. That is what we did here. This is N2 by N1 is nothing but N21. Since it is air over there, that is why we could put 1 as the number. Otherwise, there will be another N value over there and you have to take the ratio as N2 by N1. So originally, the Snell's law is either this way you can write, or you will write like this. That is N1 sin theta 1 equal to N2 sin theta 2. Or like this in terms of I and R, you can say sin I by sin R is equal to refractive index of second medium with respect to first. Now, in terms of velocity of light, refractive index can be expressed as this, n equal to c by v. That is the absolute refractive index, n is equal to c by v, where c is the speed of light in vacuum and v is the velocity of light in a given medium. So n equal to c by v we write. Now refractive index can be written in terms of wavelength. Refractive index in terms of wavelength. How will we write? So you know that n is nothing but c by v. C is nu lambda you studied. So first medium has wavelength nu lambda 1, or wavelength is nothing but the color. And nu second medium, let us imagine it is nu into lambda 2. So we have used nu, the frequency in the numerator and denominator the same, because when the ray of light passes from one medium to the other, its frequency is a constant. Okay, the frequency is a constant. So what we get, n2 by n1, that is n1 divided by n2 in this case, that is first medium's values only we wrote in the numerator. So it is lambda 1 by lambda 2. So like this we get a ratio for n1 by n2 as lambda 1 divided by lambda 2. There is another formula for finding the refractive index in terms of wavelength, that is called Cauchy's formula. So I'll write here what is Cauchy's formula. N equal to, refractive index n is equal to a plus b b by lambda square, where a and b are constants. And there is a relation between n and lambda. So the color of light questions, when asked, you can use this formula, n equal to a plus b by lambda square. Now what we can see in the next figure over here, you can see that something is there in the bottom of a tank, a coin or something, or you are putting a coin in a glass of water. Then you can see that it is raised, its image is found to be a little raised upward. The position is found to be a little bit raised upward. That is, the real object is over here, but you will see it at a point I. So this is also caused by refraction. So here in this case, sometimes the question will be to find out this shift in position. So what we have to do here is we have to use the formula n equal to real depth by apparent depth. That is the formula to be used in this case. Real depth divided by apparent depth. Real depth, for example, you are taking this as t. Okay, the full length as full width of this medium as t, and this shift in position over here in this figure, OI, you are taking OI as equal to x. Okay, then real depth is what? Real depth is t, and apparent depth is t minus x, this much only, isn't it? So total is t, and this much is the shift in position, so this will be just t minus x, so that is equal to n. So when you cross multiply and rearrange the terms, what you get as the shift in position x is, it is t into 1 minus 1 by n. So this is a shift equation which will be very useful for you for your exams. So x is equal to the thickness, the real thickness of the medium, into 1 minus 1 by n, where n is the refractive index of this medium. Usually this will be from questions will be from air to water or air to glass. Such questions will come for you. Now if there are more than one medium, what we have to do is continuously you should do the same process. Like for example, we have like this air, water, glass, air, water, glass, then air, like that it is going. Then what we have to do is you have to take the first angle and its refraction angle, that is I1 by R1, that is sine I1 by sine R1. Okay, that is will be equal to n of water divided by n of air, or you can say n NWA, second medium to the first medium, NWA. Similarly, each one we will take. The next will be sine R1 divided by sine R2. So its respective medias are Ng and W. Second medium is glass, first medium for that part of the ray is water. So it is N W NGW. Similarly, in the case of next part of the ray, that is sine R2 divided by sine I, that is again N A divided by Ng, which is equal to NAG. So if you multiply all this, what you can see is NW by NA into NG G by NW into NA by NG. Okay, so this get cancelled, NA get cancelled. What we get is, which is equal to 1. So that is the way we will find out for multiple medias how will be the refractive index comes out. Now there is a shift in position of the sun at sunrise and sunset. That is also due to refractive index change in the atmosphere. So it's actually due to the atmospheric refraction. We say the reason for this phenomenon is atmospheric refraction. So the sun, during the sunset, the sun might have gone down the horizon. This is the horizon, the level, the straight level for an observer, that is called the horizon. And the sun might have gone down the horizon. So the real sun will not be visible for this observer. But what he will see is, he will see the elevated position of the sun, like this. This case how you saw, the same way we will see here. So for 2 minutes after sunset, you will continue to see. After sunset, 2 minutes more, you will continue to see the sun. Similarly, in sunrise in the early morning, even though the sun has not come above the horizon, you will start seeing the sun's image, refracted image. Same thing is happening even there also, like a shift of position due to the refraction. We will study the portion total internal reflection from ray optics. When light travels from an optically denser medium to a rarer medium, at the interface it's partly reflected back into the same medium and partly refracted to the second medium. So this kind of reflection is known as internal reflection. At the same time, total internal reflection means it is complete reflection of ray of light into the same medium. Then there won't be any refraction at all. Okay, so in the ray of light will be completely bending back to the first medium from where it has come. That is the denser medium from where it has come, provided the angle of incidence is greater than the critical angle. Now, in this figure, you can see what is meant by critical angle. So here you can see that the first ray of light, for example, here the first ray of light, it is going through the normal, so it is undeviated. Second path of the ray, you can see that it is incidenting at angle theta 1, so it is refracting at an angle theta 2, and you can see a portion of the ray of light is reflecting too. Here what we can say is the angle of incidence has increased more than theta 1. It is called here theta c. That is the critical angle. Why it is called critical angle is because the angle of refraction in the rarer medium is 90 degree now. And beyond that, if this at this place what you can see is the angle is theta greater than theta c. Okay, so that angle change when happens, what is happening is there is no more refracted ray in the second medium. The whole of the incident ray has reflected back to the same medium. This is called a total internal reflection. So how will you define critical angle? Critical angle is the angle of incidence for which the angle of refraction in the rarer medium is 90 degree. So there are two conditions for the ray of light to undergo total internal reflection. First is it should go from a denser medium to rarer medium, for in this case N1 to N2. So the condition is N1 is much greater than N2. Then the next is the angle of incidence must be greater than the critical angle. So theta I, over here theta I is greater than theta C. Theta C is the critical angle marked in the diagram. So theta I, if you call as the incident angle over here, theta I is greater than theta C. So these are the two conditions for total internal reflection. Now we can say total internal reflection is applied in this meaning made use in different places, or we can see that in different conditions, like brilliance of diamond is due to total internal reflection, mirage is due to total internal reflection, there are total reflecting prisms. Okay, there are total reflecting prisms are there, then optical fibers are there. Okay, so all these are applications of, or the places where you will see total internal reflection. Mirage is a phenomenon we usually see in the roads, tarred roads, or in the deserts during sunny days. What is happening is, like in this figure, you can see there is a tree. This is the hot surface. Maybe it is a desert sand, or the tarred road, which is very hot. So hot surfaces are usually rarer mediums, and relatively the upper layers of air will be cooler, so that will be denser. So light is coming from a denser medium to a rarer medium, because this is cooler comparatively to the hot surface over here. So it is coming from a denser to rarer medium. And if the angle of incidence is, like as we discussed before, if it is greater than the critical angle, then the ray will bend back to the same medium. It came from air, it is bending back to air itself. So it encounters with this observer over here. So where he will see the image? He will see the image straight from his point of observation, that is over here. So what will he see is the crown part of this tree he will see, like in a pond of water. Similarly, you can see brilliancy of diamond is also due to the total internal reflection. Once the ray of light is entering the diamond, it will undergo multiple total internal reflections on its different faces. That is why cut diamond is more shining than a normal diamond which is uncut. So this cut diamonds, the faces will help in this multiple reflections inside. And most of the rays of light, because a diamond is having high refractive index n equal to 2.24, therefore its critical angle value is very less, around 22.4 only, and therefore most of the rays which are incidenting at greater than 22.4 will undergo total internal reflections here. In this total reflecting prisms, what you could see is, here there is an object. From the object, the ray of light is falling on this face of the prism, and it bends back down. So from the path of the ray of light, you can see that this AB, the upright image, is now horizontal. So that means it is turned through 90 degree. In this figure, if you see the same prism aligned in a different way, the straight upright image of a object is here, and its image is, after two total internal reflections, it becomes upside down. Here also a trapezium shaped prism we have, and we can see that AB is a object. It is undergoing multiple total internal reflection once, and it is inverting its size position by 180 degree. So this, either we can turn the ray through 90 degree, or you can turn the ray through 180 degree, either way using total reflecting prisms. So you can see this in bicycle reflectors or all road reflectors. We can see this kind of prismatic glass is used. Now other very useful place where we use total internal reflection is optical fiber. Optical fiber is used in diagnosis and treatment, as well as in telecommunication purposes for sending the signals. So here what we can say is the structure of optical fiber is such that it has a core and a cladding. Core is a denser material and cladding is relatively less denser material, a rarer material we can say. So when light enters through the core is the denser material, it goes to the rarer material and it reflects back. Multiple reflections, total internal reflections happens, and the light will reach the other end very quickly.